Hi everyone. We're going to keep looking at the reactions of carboxylic acid derivatives, and as you know, there are four main derivatives: acid chlorides, anhydrides, esters, and amides. There is that fifth beetle, nitrile. Nitrile won't be participating in all of these reactions. We are mainly going to focus on these four. And the next reaction we are up to reaction C, and that is addition of amines. Reaction Unit 6, the third reaction, C, addition of amines. Let's start out with acid chlorides. We have an acid chloride that looks like, let's do this one. Let's take a primary amine. An amine is a molecule that has nitrogen with 3 bonds. Primary meaning that the amine only has one R group, one alkyl group. Nothing else. Acid chlorides are pretty reactive. We have a good nucleophile. Not a good nucleophile, but we do have a lone pair that will act like a nucleophile. We do have a pretty electrophilic carbon that will attract that nucleophile, and we kick out the leaving group. If you recall, chlorine is the leaving group. We do want a molecule that is neutral. Therefore, we are removing the second H to make nitrogen neutral. And we did that in this case by using the chloride ion that left to pick up that second H. To organize these reactions in your head, it's probably a good idea to be really adept at naming the class of molecules. Because what we could say here is that we could verbalize acid chloride plus amines gives amides. Let me get rid of this S. Acid chloride plus amine will give an amide. Let's take a look at that ski slope that we did for video 1, just as a reminder of what we need to accomplish, what arrows we need to fill in. This is from video 1, 06A50, and I call this the ski slope. You could call this a totem pole. It just means that the top derivative is the most reactive. And I call it ski slope because it's easy to go downhill. It's easy to make an acid chloride into an anhydride. What did we do just now? We did an acid chloride, this purple arrow, all the way down to the amide. It's hard to go up the ski slope, and you can't go up directly. You have to take the ski lift. All right? So that's, again, the analogy that I like using. The next molecule is anhydride, and we're going to use this arrow to go to the amide by adding an amine. The anhydride that I want to use is going to be analogous to the acid chloride, right? We have this ethyl group. I'll make it symmetrical so it doesn't matter which carbon we attack. If we look at this first reaction, we did kick out chlorine, so we did break this bond. And in this case, we're going to break this bond. That amine is going to come in. Eventually, this leaving group is going to leave. And we'll get the neutral products. I'll do the mechanism later for the acid chloride reaction. But we get the same amide. We get the same amide because we have the same amine. And we're using a derivative that has an alpha group on the left. Okay. Same stuff on the left. Our leaving group's different though. Our leaving group was an O-, or specifically a carboxylate, but it will pick up the second H, and we could leave it like that. Again, it will be very useful if you could spell correctly, anhydride. It'll be very useful to label your classes of molecules. Going down the ski slope, we could go in ester, go from the ester to the amide. But you know that esters are less reactive than anhydrides and acid chlorides. We could deal with that by just adding heat. H2N. We don't have to do acid catalysis like we did with hydrolysis. We could just add a little heat, and this should work to get your amide again. And your leaving group was methanol. Because, oh, no, it's not methanol. It's an alpha group. So let me write it like this, actually. The line structure. Label, 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 ester. Okay. We're not going to make an amide into another amide. Remember, with ester, we were able to do transesterification, convert one ester into another, but we're not going to do the same thing for amide. Amides are pretty unreactive. All right, so it would be actually hard to do that. I don't even know what to call it. Amidation, I guess. We can't do amidation just like we did a transesterification. So we're done. Are we done? Yeah, we're done with the amines. Actually, there's one other reaction that I want to show as an aside. Let me show you how to make a nitrile from an amide. Okay, it's a little bit tricky. Let's take this amide here. And it has to be a primary amide. Primary meaning that there's only one group on this nitrogen. It has to be primary because we're going to remove water. I'm not going to go over the mechanism, but actually SOCl2, don't ask me how, will act as a dehydrating agent. And if you're going to remove two hydrogens and an oxygen, look what we have. We remove this oxygen and remove these two hydrogens. We have a C triple bond N. That's how we're going to make our nitrile. There are other ways to make nitriles. In particular, you just add cyanide to an alkyl halide. That's probably the easiest. But this is one way to make it from the primary amide. It's an aside because I'm not adding an amine to the nitrile, but I am showing you that we could take an amide that we could have made from an acid chloride, maybe, and convert that amide into nitrile. Let me make this a little more clear. Why did I put this in reaction C or reaction 6C? Because now what if I ask you how do I make this amide? Let me tell you now, I know I'm jumping a lot. I'll zoom out in just a bit. Let me tell you now that this is the best way. This is the preferred way to make an amide. So in a synthesis problem, if you have to make an amide, what should you do? Try to make the acid chloride first. Or try to get to an acid chloride, because now you could convert that acid chloride into any amide you want by picking any amine you want. Okay, so if I'm telling you that for synthesis you want to try to go through the acid chloride to make an amide, and the amide that I want to make is this, Could you figure out what acid chloride to use and what amine to use? That is the challenge. Okay? Well, the answer is this. I'll write it down here. I have to match the R group. The acid chloride I want to use is this. Remember when I added an amine, we eventually removed the hydrogen to get it back to neutral. So this piece of the amide was originally an H3. Does that make sense? Because now when I do this reaction with this amine that has no R groups, I get the primary amide plus HCl. My class, you don't have to write this, but I just want to show you where that third hydrogen went. This is an amine, but it's called ammonia. It's not a primary amine because it doesn't even have one R group. You're reacting acid chloride plus ammonia to give what? An amide, but in particular, a primary amide. Okay, and then from that primary amide, yes, you could go to the nitrile using, it's a strange, but you're using thionyl chloride. Okay, we've seen this before, but that was to put a Cl in replacement for an OH. Not in this case. Okay, we're going to do a dehydration. Yep, dehydration. Okay, that is it for the addition of amines. I got it all in one page, so let's zoom out. This is a good cheat sheet if you want to know how to make amides. Okay, and how to use an amide to make a nitrile. Let me zoom up. Okay. Next is, oh, I haven't showed you a mechanism yet. Let me show you a quick mechanism, and we're going to do the mechanism for the acid chloride. Acid chlorides are very reactive. You don't have to do anything special like protonation to get it to react. The acid chloride I have is this. Yes. And the amine I have is this. Put your dot. Go ahead and attack right away. But we're not going to kick out the chlorine. We're going to form a special intermediate. What is that intermediate? It begins with a T. Tetrahedral intermediate. From the tetrahedral intermediate, we can choose whether to remove a hydrogen, a proton, or remake the double bond. And we should remake the double bond first. This happens in real life. That happens first. And we kick out the leaving group. It's a very good leaving group. So this is a favorable reaction. And what do we have left over? We still have this nitrogen that's positively charged. But we created a Cl- that I am going to use to remove the proton to make it neutral, make the product neutral. Okay. Try to be clear with your arrows, where they start and where they end. And we have our amide plus HCl. Okay. The textbook will often say that instead of using Cl- to remove the H, you could use excess amine, and you'll have excess base to remove any hydrogen that's stuck on your final amide. A lot of times you'll see two equivalents of amine to the acid chloride, and the second equivalent is to remove that second hydrogen. But I don't mind if you draw the mechanism with only one amine and use the chloride as the molecule to remove the proton. There we go. That is the amines. The next is reaction D. And it's going to be reductions, and we're going to use a reducing agent that we've seen before, LiAlH4. We've seen it before, so let us review real quickly what LiAlH4 has done for us in the past. It's taken aldehydes and reduced them to alcohols. Here's your dot. Here's your OH. Let's label these. Oh, did I say new? I meant review. Sorry. This is review for sure. Aldehyde. Ketone. I'm just going to write the word same, meaning that you just look above and it's the same reagent. Secondary alcohol. Do you recall what happens with the carboxylic acid? We had done, in a previous unit, reduction of carboxylic acids. I'll just put Ca. It reduces it all the way to the alcohol as well. Primary alcohol. Alright. That's all review. We're going to reduce 3 derivatives with LiAlH4. The 3 derivatives are going to be the, did I say 3? Yeah, the 3 derivatives are going to be the ester, the amide, and the nitrile. We're not going to reduce acid chlorides and acid anhydrides. Let's start out with the ester. Now this is new. We had a review. Here's the new. Esters. I'll use a fancy ester with an isopropyl alkoxy group. LiAlH4. The mechanism is in the textbook, but I'm not worried about the mechanism. I'm not worried. I want you to know how to draw the product quickly. Here's your dot. Okay. We're going to reduce these carbons that are attached to oxygens. But also, a little bit strange, unless you take a look at the mechanism, you're going to cleave. So here's your dot, and you reduce it to an alcohol. But the other half of the molecule is an alcohol as well, and it looks like this. Just have to match the R group. That is how LiAlH4 reduction of esters occur. Give 2 alcohols. Now, depending on your R groups, they could be identical, okay, but many times they're not going to be identical. All right, a little twisty, right? From what we know. See, we're not just going to reduce this to the OH, we're going to reduce it to the OH and cleave. I'm trying to get all the reductions, or at least most of them, on the same page, so we could compare and contrast. Next one is amide. And the amide I want to look at is this one. We'll make it isopropyl again. LiAlH4. H2O. This one's tricky as well. Okay, it's from what we've seen before, we're likely to predict the wrong product. We're not going to cleave like we did for an ester. We're not going to make this an OH like we did for the aldehydes and ketones. Instead, let me describe this in words, and you will draw me the product. With amides, you use LiAlH4 to reduce them to amines, not alcohols, not alkanes, to an amine. All you're doing is making this amine right there. Just get rid of the double bond oxygen. Strange, I know. It's a good way to make an amine, in particular a secondary amine, because if you could make the amide with any R group you want, you could get rid of that carbonyl group, or the C double bond oxygen, and make any amine you want. Tricky, right? I'm not great at reductions, so I would definitely have to review this myself over and over again. I said that we're doing 3 derivatives. The last one is a nitrile. Nitrile. Okay. And nitrile we can use is this. Okay, you understand that there's a triple bond there between the C and the N. LiAlH4 with 2H2O. All you got to do is get that carbon-nitrogen triple bond into a single bond and put enough hydrogens so the molecule makes sense. Why am I hesitating? I'm counting the carbons. 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. Careful. Count carbons. You're not going to lose or gain any carbons in this reaction. Verbalize. Nitrile is reduced by LiAlH4 to what? An amine. More specifically, it's always going to be a primary amine. Okay? Maria, I asked you not to do that. Maria, just a second. Hey, sorry about. Am I recording? Yep, sorry about that. Maria's my cat, and she was playing with my window screen. I don't know if you could see that. And what happened was she escaped. Oop, right out the window. She knows she's not supposed to do that. Man, she broke my screen. But also, she's just chilling. So there she is, Maria. Oh, by the way, if you're kind of wondering what's wrong with her, yeah, she lost a leg. Well, not just now. She lost a leg a long time ago, so she only has 3 legs. It's a little bit hard to tell. I like seeing her fall out. Whoop. Okay. One more reaction, and it's going to be a reduction. Okay. Thus far, in this video, we saw 3 review reductions, and we see 3 new ones. Tricky, all 3 of them. Okay, you'll practice that. Maybe make a flashcard or a note card. Maybe even try to get this into a roadmap somehow, okay, with multiple cities. Maybe I'll have time for a new video at the very end of Unit 6 to do a roadmap with you guys. But one more reduction. It's kind of a weird one as well. It's using a reagent called DIBAL, and sometimes you'll see the textbook say DIBAL-H. And we're only going to do this with esters. A very specific reaction. DIBAL-H is a derivative, I shouldn't say use the word derivative, but it's a different form of LiAlH4. Let's take the ester that we've used in the previous reaction. And when we use LiAlH4, what was the trick? The trick was you identify the dot, the one that's connected to oxygen, doubly bonded to oxygen, and you cut it in half. We're doing the same thing with DIBAL. But what is different? I'll have time, I think, to show you the structure of DIBAL. But let me show you what happens. If this was LiAlH4, it would take the dot and convert it into an OH group. But here, we're going to convert it into just aldehyde. The leaving group, or I shouldn't call this a leaving group. Well, yeah, I could call this a leaving group. The other half of the molecule still remains to be a alcohol. Okay, keep an eye on that reaction. And let me go to the previous page and fold it. That could be a flashcard. What can be a flashcard? That could be a flashcard. Those two reactions. Same ester, same alcohol for the right side of the molecule. But here we go from an aldehyde, here we go to an aldehyde, here we go to an alcohol. It's a weakened version of LiAlH4. We didn't reduce all the way to the alcohol. Here we went from 3 bonds on this dot to 1 bond to oxygen of this dot. But here we went from 3 bonds to oxygen to 2 bonds to oxygen. Okay, so you could think of it that way as well. What is DIBAL? Let me remind you what LiAlH4 is first. Lithium aluminum hydride. DIBAL is this molecule but weakened. How do we weaken a reagent? We can weaken a reagent by putting bulky groups on it. Those are diisobutyl groups. It does have 1 hydrogen, so the aluminum is neutral. Diisobutyl aluminum space hydride. DIBAL or DIBAL-H. Same difference. We could think of this as a weaker version of LiAlH4. That's all I want to say for this video. I think we got through a lot, right? The only mechanism that I would expect my students to reproduce is this mechanism here for acid chlorides to amides. But honestly, if you know this, you do know the other two, right? It's the same thing, except you're just kicking out a different leaving group. Okay, and that mechanism we have over here. And then the second reaction we did today was reduction. If you zoom out, I did fit 6 reductions onto 1 page. Okay. 6 reductions right there. And then the last reaction was a new type of reduction. Instead of using LiAlH4, I used DIBAL. And then again, if you think you're going to make a mistake confusing how to reduce an ester using LiAlH4 versus DIBAL, put those 2 reactions on the same note card, same flashcard. We still have a couple more reactions to do in the carboxylic acid derivative unit. I think I could get the rest of them in one more video, and then that will be it for Unit 6. And then we could start reviewing.